ladies and gentlemen.
So let's talk conditional probability. So we've talked about simple probability before, where we just have wins over the total, or the possible number of successful outcomes over the total number of outcomes. Conditional probability plays by a different tune. Conditional probability says, if we fix the probability of something else, what's the probability of this event occurring? So a common example would be in a deck of playing cards. What is the probability that we draw an ace given that the card is a red card? Or what's the probability of the card being red given that the card is a queen? What's the probability of the card being red given that it's a diamond? You can see that some of those probabilities are different than your standard 1 out of 52, which is the probability of drawing any given card from the deck of 52. So how do we play with conditional probability? Typically, we play with them using two-way tables. In this two-way table, we have some properties. The actual amount listed in a two-way table, the number, is called a conditional frequency. So that's one of our vocab words we're going to have. So if I'm saying that I have one card that is both a jack and a spade, then the conditional frequency of spades that are also jacks is 1. But that would change depending on how I define the categories. The notation that we're going to end up using for conditional probability looks like this. It's the probability of A vertical line B. We pronounce that as the probability of A given B. Now, we talked about independent and dependent in the last video. If these two categories have nothing to do with each other, if we're rolling dice and flipping coins, then the given part doesn't change anything. What's the probability of flipping a heads given that you rolled a 4 on a standard D6? It's still 1/2. It doesn't change. But talking about our playing cards, that does change because those are dependent. So if you get the same probability, no matter what the second category was, just means that those two events were independent of each other. The last thing I want to talk about before we dive into a problem is what happens when we have these two events and we're talking about something other than just given, that one happened given another. Well, if we want to find the probability of A and B occurring, we look at that situation, we kind of figure out what happened there. The probability of rolling a 4 and flipping a heads would be the 1/6 and the 1/2 being multiplied together. That makes sense. But what if it's rolling a 4 or flipping a heads? Then it becomes a little tricky. How we actually figure that out is we use this formula here, which looks daunting, I know, but it's a formula, which means that each part just means something. This U shape stands for union. For our intents and purposes, this means or. This one, the upside down U, stands for intersection. For our case and purposes, it stands for and. So and means that both have to be true at the same time, or means that one could be true or the other one could be true at any given time, and it still works. They both could be true, one could be true, the other could be true, and all of that produces a true statement. But if they're both false, then it doesn't include it. How we find this probability is we take the probability of whatever A is, add it to the probability of B, and subtract any overlap. If I'm talking about two events that have nothing to do with each other, so if I'm talking about rolling the dice and flipping the coin, there is no overlap. That doesn't make any sense. The probability of rolling a 4 and the probability of flipping a heads don't have anything to do with each other. There really isn't any overlap there. But if we are talking about more exclusive events that are dependent upon each other, there is going to be an intersection. You have to remember to subtract that. Don't worry, we're going to play around with it. So let's get started. So I do want to apologize. There's a lot of information all here all at once. So let's take it step by step. We're using the same data for all of these questions. So we have two categories. We have the amount of education someone has, and then we have gender, men and women. Then we have specific numbers. So remember, these are called conditional frequencies, since we've split these two categories and these are the intersections of two different data points. We also have totals. So the total number of men was 100. The total number of women was 109. The total number of bachelor degree people is 42. So you get an idea of how this chart plays with the data. So using this, we're going to answer some questions. What is the conditional frequency of a man with a high school diploma / GED or less? Well, high school or GED with a man would be 47, but we could also have less, which means the no high school diploma or GED, and that would be 12. So we're just going to add the numbers together, and it's just the number. So 7 plus 2 is 9, 4 plus 1 is 5, so 59 would be that conditional frequency. Remember, we're not talking about probability there. The next one, what is the probability of randomly selecting a woman with an associate's degree? Well, women with associate's degrees are 12, so that would be a 12. We did not restrict ourselves from any of this, so we are pulling this person out of the whole 209 people sampled. The next one, what is the probability of randomly selecting a person with an associate's degree given that person is a woman? So what that means is that we don't look at the men column at all. We are only looking at the woman column. So that means that associate's degree with a woman would be 12. That didn't change from the last problem. But instead of the 209, we're restricting ourselves to only women, which is the 109. So instead of 12 out of 209, it's 12 out of 109. So that's the difference, is the denominator changes for a lot of these. What's the probability of randomly selecting a man with more than a high school diploma / GED? Since it says more than and not inclusive, it means that we do not include the high school diploma. We only care about people who have college degrees of some sort. So men with college degrees would be 9, 20, and 12. So 9 and 20 is 29. 29 and 12 would be 41. So this is 41. Did we restrict ourselves? Well, we don't have given anywhere, so we didn't. So this would be out of the 209 total people. Now, what is the probability of randomly selecting a man given that they have less than a bachelor's degree? Well, we are restricting ourselves to less than a bachelor's degree. So that would be 24, 97, and 21 as our picks. We're completely excluding people with a bachelor's degree and a graduate degree. So 24 and 97, I can borrow 3 here, make this a 21, make this a 100. 21 plus 21 is 42, plus 100 would be 142. Now, what's the probability of selecting a man given that information? Well, we got to pick our men from that situation. So 12, 47, and 9. If I borrow 3 from the 9 to give us 50, 12 plus 6 is 18, plus 50 would be a 68. So that would be 68 out of 142 possible people. Let's erase our modification on the chart. What is the probability of randomly selecting a person with less than a high school diploma given that the person is a woman? So we are restricting ourselves to only women. And what's the probability of selecting a person less than a high school diploma? So that would be no high school diploma. That would be 12 out of the 109 possible women. So the given tells you what the denominator is going to be. The probability of what we're looking for is going to be the numerator. So, what is the probability of randomly selecting a woman given that they have less than a high school diploma or GED? So, we're switching the denominator here. We still have 12 successes, women with no high school diploma. But instead of 12 out of 109, we're not talking about just women. We're talking about just people without the high school diploma or GED, so it's 12 out of 24. Now, to spice things up a little bit, what's the probability of selecting a person with a graduate degree or a person that's a woman? Well, the probability of selecting a person with a graduate degree would be 25 out of 209. 25 out of 209. The probability of selecting a woman is 109 out of 209. The probability of the overlap would be 13 out of 209. So because we counted this 13 twice in the 25 and the 109, we have to remove it. So 109 minus 13 might be, well, you know what? Scratch that. 25 plus 109 would be 134. And if we subtract 13 from that, that gets us 121 out of the 209, and that would be our probability. So, not too hard. It's kind of common sense in some respects. I can see where it could be difficult, but hopefully we're making it our own, and we're not just relying on memorizing all of these lovely formulas that we have. But main key takeaway is that conditional probability means that we are restricting our pool of applicants, you can think of it that way, where the denominator of our probability is going to change, and the probability of an or is one, the other, minus the overlap. So if you've got that down, you'll be awesome. If you have any questions, let me know. Otherwise, I look forward to seeing you in the next video.